Today we are going to talk about periodic functions. There are so many processes in life that they repeat themselves. A pattern which repeats itself, we call it periodic. Examples of periodic functions in life are sounds out of a band, when you start up the car, the idling of a car, the phases of the moon, because it repeats itself every 12 months, and your heartbeat. They all have something in common that we call period, and they are periodic because they repeat themselves. If you consider this graph, you can see that this function is just repeating the same pattern. The pattern, you can look at it this way, that it starts from the minimum, then it goes to 0, the midline, then it goes to maximum, then it goes back again to 0, minimum, 0, maximum, and so forth. This is what we call a periodic function. It's just repeating itself. Now, all these points we call the maximum of the function. All these points we call them the minimum of the function. We define a cycle to be a complete repetition of one pattern. For instance, here it starts from 0, goes to the midpoint, then goes to a maximum, comes back to a midpoint, and then gets back to minimum. This is called one cycle of this function. Now, if you look at the next cycle, the same thing happens. We start from 0, midpoint, maximum, midpoint, and 0 again. Now, the time that it takes for one cycle to happen, the horizontal length is called the period. For instance, the distance from here to here is called the period, or from here to here is called a period. And as you can see from the graph, the period of a periodic function is the same. In general, we define a periodic function to be a function that has a pattern of y values that repeats at regular interval. If you look at the previous example, you can see that the y values, they follow the same pattern, and it happens at the regular interval. Again, y, let's assume this is the minimum, which is 0, then it goes to a midpoint value, then to a maximum, again to a midpoint value for y, and then to 0. This is a property of periodic function. Now we define another term which is called the amplitude. We define the amplitude, A, to be the halfway distance between max and mean. If you look at this graph, you can see that this point here is the max, and this point here is the mean. We define amplitude. How you find it? Very simple. You say max minus mean divided by 2. So the amplitude is the distance between max and mean, and the way you find it is we are going to subtract mean from max, and then we divide it by 2. Let's do a couple of examples. The first one, it says that we have to check each graph and determine whether the function is periodic, and if it is, we have to find the period. The first one is A, which is this function. If we look at the graph, you can see that the function repeats itself, the graph. How do we know that? It's very simple. You can see that the function starts from 0 here, it goes up to here, down, and then it gets to this point, and then it starts repeating. Or we can go left. We can say that it starts from this point, goes up, down, and gets to here, and again it starts repeating. So we say, yes, this is periodic, and the period is the time it takes for one cycle. Our cycle starts from here and it ends here. And if we look at the horizontal distance is 6 seconds. Or we can say our cycle starts here and it ends here. Again, the distance is 6 seconds. The second graph, if you look at the graph, you can see that there is no repetition here. You cannot find any part of the graph which repeats the next period. So we say that this graph is not a periodic function. There is no pattern in the y values which repeats itself. The next example, again, we have a graph. We have to determine if it's a periodic, and if it is, we have to find the period. We can easily see that the function repeats itself. For instance, if I take this point to be the start point, then the function goes up to this point, then goes down, goes under the x value, and ends here. So I can see that again the next time to the right here, the function is repeating itself the same way. So we can say that this is periodic. The period of the function is 4 seconds, which is here. So the period is 4 seconds. And the amplitude by definition is max. The max value here is 3 minus the mean value is -1, so -1 divided by 2, which is 3 plus 1 divided by 2, which is 4 divided by 2, which is 2 units. The next example, we have a periodic function given on the right. We are supposed to find the period. To find the period, again, we are going to do the following. We are going to start from a point on the graph and then find the next point where the graph repeats. If I start from this point, let's say, then I can see that this is the end of the graph, which after that the graph is going to repeat itself. So I can see that the period is going to be this distance, and this distance is 6 seconds. So the period is going to be 6 seconds. The next part of the example asks what is f of 2. From the graph you can see f of 2 is going to be this point. So we can say that f of 2 is going to be equal to 1, and f of 5 is going to be this point, which is going to be equal to 0. The next example, it says predict f of 8, f of -10, and f of 14. If we look at the graph again, you can see that 8 is off the chart. F of -10 is also point -10, is going to be somewhere around here, which is off the chart, and also f of 14 is going to be somewhere to the right, which is not possible to see. But the way we can find it is we can use the property of periodic function. Remember, the periodic function is a function that repeats itself. The y patterns are going to be repeated every period. And we know that the period of the function is 6 seconds. So we can use this fact and we can predict the values of f of 8, f of -2, and f of 14. To do that one, I'm going to use the following fact. For instance, for f of 8, I know that f of 8 is the same as f of 8 minus the period. Remember, whatever the y value is going to repeat itself every period, which is 6 seconds. So either I go to the left, f of 8 minus 6, or I can say f of 8 plus 6, which is the same as f of 8 plus 2 times 6, 2 periods to the right. Or I can go 2 periods to the left, and so forth. This means that f of 8 is the same as f of 2. But we know f of 2 from the graph is going to be 1. So we can say that f of 8 is equal to 1. Now for f of minus 10, I can write f of minus 10 is the same as f of minus 10 plus 6, 1 period to the right. Now this is equal to f of minus 4. F of minus 4, from the graph you can see that it's equal to this point, which is going to be 1. Now we have to find f of 14. F of 14 is the same as f of 14 minus 6, 1 period to the left. But this is f of 8. Unfortunately, we cannot see point x equal to 8 on the graph. So I'm going to go 1 period to the left again. So I'm going to say f of 8 minus 6. F of 8 minus 6 is equal to f of 2. And from the graph, we can see f of 2 is equal to 1. So although we did not have the graph to the right and to the left, but we could use the properties of periodic function to find the values of points which are not shown on the graph, or we could predict the values of the function. The next part of the example is what is the amplitude of this periodic function. You can easily see that the maximum here, this point, has the y value equal to 3, and the minimum here has the y value equal to negative 2. So the amplitude is max minus mean, which is negative 2 divided by 2, which is 3 plus 2 divided by 2, which is 5 divided by 2, which is 2.5 units. The next example is asking find 4x values such that f of x is equal to 2. So I have to find x's such that f of x is equal to 2. You can find that looking at the graph is that f of 0 is 2. So we know f of 0 is 2. Now if I want to find 4x values such that this is true, then we use the fact about periodic function. The function, the y values repeats every period. So since the period of this function is 6, I can say that f of 0 is f of 0 plus 6 is equal to f of 0 minus 6, doesn't matter right or left, or f of 0 plus 2 times 6, or f of 0 minus 2 times 6, 2 periods to the left, which is equal to f of 0 plus 3 times 6, and so forth. Now, 0 plus 6 is going to give me 6, 0 minus 6 is minus 6, 2 times 6 gives me 12, this one negative 12, this one 18, and so forth. So for f of x to be 2, x is equal to 0, negative 6, 12, negative 12, 18, and so forth. The next example, we have a graph which shows the usage of natural gas in Ontario per month beginning in January 2001. This means that it starts here in 2001, and then in 1 year, after 12 months, it gets to here. Now, the first question says, explain why the graph has this shape. Since January is in the winter and it's a cold month, the amount of natural gas which is used is going to be very high, so that's why we have a high point here. The midpoint, which is here, is going to be approximately in the summer when the weather is warm, so the amount of gas used is going to be lower. And then when it gets again to the end of the year, which is month 12, again it's going to be winter, so the amount of gas used is going to be higher. So that's why the graph looks like what you see on the screen. And this obviously shows you a periodic function because it almost repeats itself. The next question wants us to explain if this data appears to be periodic, and we have to justify our answer. As you can see, it's almost periodic, not exactly, but it looks like a periodic function. The next part of the example says, assume that the consumption of natural gas can be modeled using a periodic function. Determine the approximate maximum value, minimum value, and amplitude of this function. Now, if we look at the function, the graph, you can see that the maximum value is approximately 1.6 million cubic meters, and the minimum value is around here, which is about 200,000. So the minimum is 200,000 cubic meters. And the amplitude by definition is max minus mean divided by 2, which is 1.6 million minus 200,000 divided by 2, which is going to give us approximately 700,000 cubic meters of gas. The next part of the example says, estimate the period of this function, and does this value make sense? And we have to explain. Now, if we look at our graph, we can see that one period of the function starts at this point, which is the maximum, and ends at this point, which is another maximum. And if we find the distance from here to here, we can see that distance is 12 months, which makes sense because 1 year is 12 months, and the pattern repeats. If we start from winter, in 12 months we're going to end up in winter again. The next two parts of the question, part E says we have to find domain and range of the function, and also part F says explain how the graph can be used to estimate the natural gas consumption in February 2011. The first part, for the domain, we can see that our x values, they change from 0 to 60, so we can say that the domain is x in R, and x less than or equal to 60, greater than or equal to about 1. 1 meaning month 1. And the range is y in R, and y is between maximum and minimum, which is 1.6 million to 200,000 cubic meters. So this is our domain and range. Now, the next question was, we have to explain how we can use the graph to estimate the natural gas consumption in February 2011. Since 2011 is off the chart and it's going to fall somewhere around here, but we know that this is almost a periodic function, not exactly a periodic function. What we can do is that we can find the gas consumption in February for 60 months, okay? And then we can just take the average of all those gas consumptions. So this means the following. We know that February's x is equal to 2. So we are going to find the y value when x is 2 for up to month 60, which is available on the graph. Then what we do is that we are going to take the average of all these values to find what is going to happen in February 2011. And that's one of the properties of periodic function. We can use the fact that the y value repeats. We can predict the value later on.